Have you noticed something strange about the AI race lately? Every few months, another company announces a bigger chip, a larger data center, or a machine that consumes enough electricity to make your neighborhood's power bill nervous. The industry's solution has basically been, need more AI? Throw more hardware at it. But what if that entire idea is backwards? What if instead of buying thousands of expensive chips, you could make the ones you already have work dramatically better? That's exactly what a research team from Peking University set out to prove. And instead of designing some massive next-generation processor, they focused on something most people never think about: how chips communicate with each other. Now here's where things get interesting. Their experimental system completed a specific AI task almost 149 times faster than a conventional GPU setup, even though its total computing capability was only about 1/9 as powerful on paper. That sounds impossible, until you understand what was actually slowing modern AI down. Most people assume AI spends all its time calculating. It doesn't. A surprising amount of time is spent waiting. Waiting for data. Waiting for memory. Waiting for another processor to finish. It's like having 5 world-class chefs in a kitchen where only one cutting board exists. The chefs aren't slow. The kitchen is. Modern AI chips can perform trillions of calculations every second. But before they can solve anything, they need data delivered from memory or another processor. Moving that information through electrical connections creates delays, heat, and massive energy waste. Engineers even have a name for this bottleneck: the memory wall. For years, the industry has tried solving this problem by adding faster memory, wider connections, and increasingly complex chip designs. Those improvements help, but they still rely on electricity traveling through copper wires, and physics eventually says, that's enough. So instead of making the processors faster, the Chinese researchers asked a completely different question. What if the data didn't travel through wires at all? Their answer wasn't another GPU. It was light, and that single idea could completely change how future AI systems are built. So, how do you actually make chips talk using light instead of electricity? This is where the project becomes genuinely fascinating. Instead of relying on one giant processor to handle everything, the researchers divided the AI model into 5 separate stages. Each stage ran on its own FPGA, a programmable chip that can be customized for a specific workload instead of acting like a general-purpose GPU. Think of it as building 5 specialists, instead of hiring one person expected to do every job. But the real breakthrough wasn't the FPGA itself. It was how these chips communicated. Every FPGA was connected to a custom optical transceiver. Before data left a chip, the transceiver converted electrical signals into light. That light then traveled through an optical switch before being converted back into electrical signals for the next processor. Instead of sending information through traditional copper connections, the system literally moved data using beams of light. Why is that such a big deal? Because electricity has limits. Push electrical signals faster through copper, and resistance increases. More resistance means more heat. More heat means bigger cooling systems, higher energy bills, and eventually a point where adding speed becomes incredibly difficult. Light doesn't suffer from those same problems. Different wavelengths of light can travel through the same optical fiber simultaneously without interfering with one another. That allows enormous amounts of data to move with very little signal loss, even over longer distances. The team's optical transceivers supported 400 gigabits per second of communication, while their central optical switch was designed to connect up to 16 processors, leaving room for future expansion beyond the 5-chip demonstration. But speed alone wasn't the magic. The researchers also redesigned how the AI workload moved through the hardware. Instead of making one processor finish a task before another could begin, every FPGA handled its own dedicated layer continuously. As soon as Chip 1 finished processing a piece of data, it immediately passed it to Chip 2 and started working on the next input. Seconds later, every processor was active simultaneously. Imagine a perfectly synchronized assembly line where no worker ever stands around waiting for parts to arrive. That's exactly what this system achieved. By combining optical communication with a non-stop processing pipeline, the researchers removed much of the waiting that normally slows AI systems down, and that's the secret behind the astonishing performance numbers we'll break down next. Now comes the moment that grabbed headlines around the world. Did this optical system actually outperform a powerful GPU? According to the research team, yes, but there's an important story behind those numbers. To test their design, the researchers didn't choose a giant language model or a chatbot. Instead, they used a 5-layer AI model trained to clean noisy images from the Fashion MNIST dataset. Each image measured just 32 by 32 pixels, and the model had already been trained beforehand. In other words, this experiment focused on AI inference, using an existing model, not training one from scratch. The team processed 1,000 images through their optical pipeline. The result? The entire workload finished in roughly 105 microseconds. To put that into perspective, a microsecond is 1/1,000,000th of a second. Blink, and you've already missed millions of them. What's even more impressive is how efficiently the system operated. Although the 5 FPGA chips delivered only about 1.97 teraflops of theoretical computing power, they achieved nearly 95% hardware utilization. That means almost every bit of available processing power stayed busy doing useful work instead of waiting for data to arrive. Then came the comparison everyone was waiting for. The researchers ran the exact same AI task on a conventional GPU capable of approximately 16.96 teraflops, over 8 times the raw computing performance of the FPGA setup. On paper, this shouldn't have been close. Yet the GPU completed the task in about 15.6 milliseconds, while the optical pipeline finished dramatically faster, making it nearly 149 times quicker for this specific workload. So, what happened? The answer isn't that the GPU suddenly became slow. It's that the GPU spent a surprising amount of time doing everything except calculations. After completing one layer of the model, it had to write intermediate results to memory, prepare the next layer, reload data, and repeat the process. Every one of those steps added tiny delays, and together they became the biggest performance bottleneck. Meanwhile, the FPGA pipeline never stopped moving. Each processor permanently handled one layer, data streamed continuously over optical links, and every chip stayed active almost the entire time. The lesson here isn't that GPUs are obsolete. It's something much more important. Raw computing power means very little if your hardware spends most of its time waiting instead of working. And that's the real reason this experiment caught the attention of the AI industry. So, does this experiment mean Nvidia is finished? Not even close. And that's exactly where a lot of headlines get the story wrong. This research didn't prove that a handful of FPGA chips can replace every GPU in every AI data center. The system wasn't tested on massive language models, video generation, or large-scale AI training. Instead, it demonstrated something much more valuable: how smarter system design can unlock far more performance from existing hardware. The researchers used a relatively small 5-layer model that had already been trained. Their optical pipeline was carefully optimized for that specific workload, which is very different from the unpredictable mix of AI tasks handled by today's cloud platforms. GPUs remain incredibly flexible. They can switch between countless models and applications without needing to redesign the hardware. But here's why this breakthrough still matters. As AI models continue to grow, companies aren't just fighting for faster processors anymore, they're fighting against communication delays. Imagine a relay race where every runner is getting faster each year, but the baton handoff never improves. Eventually, the handoffs become the slowest part of the race. That's exactly what's happening inside modern AI clusters. Thousands of processors constantly exchange information. As individual chips become more powerful, the time spent waiting for data starts eating away at those performance gains. Simply buying larger GPUs doesn't solve that problem forever. That's why optical communication is attracting so much attention across the industry. The real opportunity isn't replacing powerful processors. It's making sure they spend less time sitting idle. If future systems can combine specialized hardware with high-speed optical links, AI data centers could process more work while using fewer resources. For companies running the same AI models millions of times every day, that could translate into significant savings in cost, energy, and response time. So the biggest takeaway isn't China built a chip that's 149 times faster. The real story is that they demonstrated a different way of thinking. Instead of chasing bigger processors, they focused on eliminating the wasted time between processors. Whether this approach eventually scales to hundreds or even thousands of chips remains to be seen. But if it does, the next leap in AI performance may come not from adding more computing power, but from making every existing processor work together far more efficiently. And sometimes the biggest technological breakthroughs don't come from building a stronger engine. They come from clearing the traffic that's been slowing the engine down all along. And that's what makes this research so exciting. It isn't about replacing every GPU tomorrow. It's about proving that smarter engineering can sometimes beat brute force. In tech, bigger isn't always better. Sometimes it's just a bigger electricity bill. Imagine buying the world's fastest sports car only to spend every day stuck in traffic. That's exactly what happens when powerful AI chips waste time waiting for data. The future of AI may not belong to whoever builds the biggest chip, but to whoever builds the smartest system. If you enjoyed this deep dive, hit that like button, subscribe, and let me know in the comments. Would you bet on faster chips or the speed of light?